Our first sort of inaugural speaker for this seminar series is Dr. Jiang, a longtime friend and colleague of mine now at the University of California, Davis. So Jiang got his PhD in 1995 from UC Berkeley, working with Peter Bickel in the statistics department. He then was on faculty at Case Western Reserve University in the stat department until 2001, and that's where we hooked up together and started doing some work together. In 2001, he left to go to UC Davis, and he's been a professor of statistics there since. He's very well known in a number of different areas of statistical modeling. So I wrote down a bunch of them here, but mixed effect modeling, generalized linear models, model selection, small area estimation, asymptotic theory, longitudinal data analysis, matrix algebra, numerical analysis. There's a variety of different things that he likes to fool around with. So he is a fellow of the Institute of Mathematical Statistics. He's a fellow of the American Statistical Association. He's an associate editor for the Annals of Statistics, an associate editor for the Journal of Multivariate Analysis, and he's, I guess, the editor, coordinating editor for a new journal called the International Journal of Statistics and Management Systems. So, without further ado, I'd like to welcome Jiang.
Well, thank you very much for the very nice introduction. And this is the first time I've been in the city of Miami, although I've been in Florida a couple of times before. Of course, we all have heard about the Miami hurricanes, and I was just told that they have the season opener today. So I looked a little bit of search on over the internet and found this little website is currently ranked number 13 in the country. But this is just beginning of the season. You know, they used to win the national championships, so who knows what's going to happen at the end of the year. But anyway, wish them the best luck, and the national championships will be back soon. Okay. So. Yeah, but actually, recently I've been paying much more attention to the University of Miami since my longtime collaborator and friend, Dr. Sunil Rao, moved to University of Miami. I noticed that the university now is one of the top 50 national universities. Congratulations on the move on the national rankings. And also the city of Miami is hosting the next year's joint statistical meetings. So that's a big event for statistics and also biostatistics, I guess. I don't quite remember we had any of the joint statistical meetings in Palo Alto or Berkeley, even though it's the top statistics department in the country. So it's certainly a big event. Well, here is the talk. Let me make it a full screen so we can view it a little bit better. It's a joint work of Dr. Rao and myself and one of my former students. This title is called Invisible Fence and methods and identification of differentially expressed gene sets. So I guess this term that fence is probably the one that catches your eyes, but I have to explain that a little bit so we know what the fence method is. So basically, it's a method that is recently developed for model selection. Okay, so later I'll try to build a connection between model selection and the gene sets identification problem. But right now, let's just think about fence as a method for model selection. Now here are a few more descriptions about this method. So what is the idea of fence method? Well, it involves a procedure to isolate a subgroup of what are known as correct models, of which the optimal model is a member. This isolation of the subgroup of model is accomplished by constructing a statistical fence or barrier to carefully eliminate incorrect models. So the name actually comes from here because this involves the construction of a statistical fence. Once the fence is constructed, the optimal model is selected from amongst those within the fence according to a criterion that can be made flexible. So you say, what is this all about? Well, let me give you a simple example to illustrate the idea of the fence. Let's say we are dealing with a regression variable selection problem. Okay, so if someone tells you, okay, I got 1,000 potential variables from which I want to select a best subset of variables. Okay, this is a typical regression variable selection problem. Okay, so then another person says, well, here I found two models. Okay, one model has 3 variables. Okay, the other one has 100 variables. Okay, now these two models perform almost the same in terms of model fitting. Okay, so you say, well, how do you measure model fitting? Well, you could look at the residual sum of squares. Okay, after fitting each model, you look at their residual sum of squares and find that these two models perform almost the same with the larger model, the one with 100 variables doing slightly better, okay, in terms of model fitting. So then the question is, which model is better? Okay? You know, the model with 100 variables isn't necessarily better, even though it fits slightly better, right? Because there's some other criteria that people would like to take into account. Okay? So now, if you construct a statistical fence, then it is possible that both models will fall into the fence. Okay? So then the question is, which model are you going to select? Okay? So this is the next step of the fence method. So from the models within the fence, okay, once the fence is constructed, you're going to select an optimal model from those models within the fence. Okay? And that selection criterion can be made flexible. Okay? For example, one of the criteria that is often used is the minimum dimension criterion. Okay? Basically, you select the model that has the smallest number of variables. Okay? So you can say the minimum dimension of the model. So in this case, the model with 3 variables is preferred to the model with 100 variables because of its simplicity. Okay? Both models in the fence, but the model with 3 variables is much simpler. Okay? So here, your criterion of optimality is minimum dimension. But you can change that to something else that incorporate with your practical interest. Okay? For example, you may say, okay, here I got a model involves a variable that is not easy to measure. Okay? But there's another model which does not involve that variable. Okay? Both models in the fence. Okay? Now, personally, I prefer the model without using that variable because this will perhaps more cost effect. Okay? Because it doesn't involve the variable that is not easy to obtain information from. Okay, so that's just an example. You have this flexibility as another advantage of the fence. Okay, so now here's a little technical description about how to construct a statistical fence. So basically, we're looking at this inequality. On the left-hand side, is a difference between Q hat M and Q hat M tilde. So what are these things? Well, Q hat M is a measure of lack of fit. Okay, for example, you may think of of the residual sum of squares in the regression setting. Okay, so think about the regression sum of squares. That's a measure of lack of fit. Okay, so this is the QM, but this can be general. It can be more general than residual sum of squares. Now, what about this term? This is the baseline measure. Okay, basically, this is the smallest residual sum of squares. You can think of it that way, but it doesn't have to be the residual sum of squares. For example, if you have, going back to that example that I gave earlier, that involves 1,000 variables. Okay, if you fit a regression that involves all the variables, you will get the smallest residual sum of squares, and that will be the baseline. So this guy is the baseline measure. Okay, so what? On the right-hand side, you have a constant C that is considered as a cutoff. Okay, so basically, this inequality is saying that I want my measure of lack of fit to be good enough in the sense that it is close enough to the baseline measure. Okay, so as long as this model fits good enough, meaning that it's within a striking distance from the baseline measure, I consider that model as being in the fence. Okay, so this is what we call the fence inequality. So then you say, how do you determine this cutoff? Okay, it seemed to me that this cutoff is very important because it determines who's in the fence and who's not. Okay, so it's like a life and death. So how do you determine the cutoff between life and death? Well, there's some procedure to select this constant adaptively, which I'll illustrate with a little plot in my next slides. So this constant C can be determined, can be chosen either as a fixed or adaptively. Now this illustrates our simulations results show that the adaptive method, when you choose this cutoff adaptively, the finite sample performance can be significantly improved. Here's a little illustration on how you select how you would select the cutoff adaptively. So basically, you let the data tell you what is the best cutoff. Then you say, how am I going to do this? And how can I make the data speak? Well, here's the idea. This is the plot that shows the empirical probability of the most frequently selected model when you have different cutoffs. Okay, so what you do, you change this, you consider different cutoffs, and at each cutoff, you can calculate the empirical probability of the most frequently selected model. Okay, this is the model that is most supported by the data, but it changes with the cutoff. Okay, so somewhere in the middle, there is a peak. There's a highest point, there's a cutoff that corresponds to the highest empirical probability, and this is the adaptive choice. Is our choice of the cutoff, which we call adaptive choice of the constant C. So this plot is quite typical. Usually it's a W-shaped. Okay, so you may wonder, you can tell that when the cutoff is 0, the highest empirical probability is equal to 1, and also when this cutoff is very large, the empirical probability is also very close to 1. So you may wonder, why is this happening? Okay, why is it W-shaped? Well, here's the reason. Okay, so when the cutoff is 0, then you basically have no choice. Why? Because here's why. So here's the fence inequality, right? If C is 0, the only choice you can have, every time you have to choose the baseline model, because you want this thing to be exactly 0. Okay, so because nobody can do better than the baseline model, but there is a model that does exactly as well, and that's the baseline model itself. Okay, so when the C equal to 0, every time you make a model selection, you always choose the baseline model. So that probability is 100%. Okay, so that's why the empirical probability is 100%. Okay, you don't have a choice. Okay, and also when C is very large, once again, you don't have a choice. Why? Because, for example, let's just consider this quite minimum dimension criterion. Okay, if C is very large, then what happens is that every model is in the fence, because C is a very large number. Everybody satisfies this inequality, so everybody's in the fence, right? So then, how do you select a model how do you select among the models within the fence? Well, you say we choose the model that is the simplest. Okay, so then here we go. So every time you choose the simplest model, regardless how the model fits the data, because you always choose the same model, which is the one with the minimum dimension. So again, you don't have a choice. Every time you choose the model with the minimum dimension, that is why the empirical probability is equal to 1. Okay, so basically this illustrates how to choose the cutoff adaptively. Now, one critical assumption of this method that was originally proposed by this paper, published in the Annals of Statistics, is that there exists a true model among the candidates. But this assumption, although it's necessary in establishing consistency of the model selection, it limits the scope of applications, because in many cases, the true model may simply not exist, or exist but not among the candidates. How could you know that the true model is among the candidates? In many cases, this is not practical, right? So the question is, can we use the fence method without this assumption, okay, without requiring the existence of a true model among the candidates? And this would be the case, in particular, for the problem of microarray gene set analysis discussed in the sequel. Right. So now let me introduce a motivating example. Here's a main motivation for our gene set identification problem. So it's a data set involving a data set used in a study in tracking pathway involvement in late stage versus early stage colon cancers. Basically, we have microarray gene set expression data from 4 distinct colon tissue samples. So these are the 4 different colon tissue samples. So these were collected. So then the actual data set consists of 104 samples, of which 25 were B survivors, 21 were Duke Cs, 35 were Duke D, and 23 were liver mets. And these were all collected at the Ireland Cancer Center of Case Western Reserve University, where Dr. Rao used to collaborate with some scientists over there. There were a total of 59,618 probe sets or genes. So these are so this is a brief description of the data. So then one question of particular interest to colon cancer biologists is to see which colon cancer specific pathways. Here by pathways we mean groups of genes acting in concert with one another seem to be at play when comparing a bad prognosis tumor to a relatively good one. And understanding which pathways are differentially expressed gives a better picture of the biological processes that might be at play in worsening prognosis. So basically, this is the motivating example, which I'll come back at the end if I have time. So now, once again, as I mentioned, in order to apply our method, more specifically the FANS method to microarray gene set analysis, we need to extend the FANS method to the situation where a true model may not exist. Okay? The extension can be done, but it involves a little bit technical treatments or mathematical definitions. So what I decided to tell you briefly the idea of the extension, then I'll skip the details. Okay? So basically, it's all about how you define the term true models. Okay? So if you define the true model in terms of the traditional sense, traditional definition, so then you run into this trouble of having to worry about the existence of true model. Okay? So now, if you define a true model in terms of the model that best fits your data, then such a model always exists, right? So in a way, that is not necessarily a true model in the traditional sense, but the one that can be best approximated. Okay, so this is the definition. Okay, so you have a group of candidate models, okay, among which there is a one that best approximate your data. Okay, so this is what we call the true model. Okay, but this one may not be the most efficient one. Okay, so that's why we need to do a model selection. Okay, so this way you extend the notion of model selection or true models, and therefore avoids the requirement for the existence of true model, because such a true model always exists. Okay. So some technical terms which I'll skip. Right. So now let me go back to the microarray gene set analysis. There have been studies on the problem of identifying differentially expressed groups of genes, which we call gene sets, from a set of microarray experiments. One of the papers is this one, which I discussed with one of the faculty members earlier today. So basically, these problems are fairly practical from many of the recent studies. In particular, there's this paper by Efron and Tipshrani, published in 2007, in which they propose a method called gene set analysis, or GSA, based on testing the significance of gene sets. Now, the method proposed by this paper is called GSEA, gene set gene expression enrichment analysis. Well, this one is called gene set analysis. So there's one letter difference, but the methods are different. And Efron and Tipshrani claim that their method performed better than GSEA based on their studies. Now here's the problem. Formulated in a mathematical formation. Suppose there are n genes, capital N genes, measures on small n microarrays under two different experimental conditions called control and treatment. The number of genes is usually large, say at least a few thousand. while this little n, which corresponds to the sample size, is much smaller, say 100 or fewer. Now, the interest is to assess the significance of some predefined gene sets rather than individual genes in terms of response to the treatment. The gene sets are derived from different sources, such as biological pathways. Here's a description of the GSA procedure. So first you compute a summary statistic for each gene. For example, the two-sample T statistics. Two-sample T statistic. So then, based on the gene set, based on the gene-wise statistics, you come up with a gene set statistic for each gene set. That is computed for each gene set based on the summary statistics. For example, you can take the average of all the summary statistics within that gene set. Okay, this gives you a gene set statistic. The next step is called restandardization. You do this by subtracting the gene-wise mean of the summary statistics from each gene set statistic, and then dividing the difference by the gene-wise standard deviation of the summary statistics. Results of the restandardized gene set statistics are called gene set scores. The p-value for each gene set score and the false discovery rate, or FDR, applied to those p-values are then estimated by permutations of the class labels in the control and the treatment groups. Depending on the FDR, a number of gene sets may be declared significant, or no gene set is declared significant. So this is a description of the GSA method. So now, so our goal is to take another look of the FANS method, and this will allow us to be able to use our method for the current problem of gene set identification. Now here's the another way to look at the FANS method. So basically, you ask yourself the question of how to choose a model within the FANS. Okay, I'm going to make it a little bit simpler. Let's just say, remember there's a criterion of optimality to choose the model within the FANS. Okay, so let's just say the criterion is the minimum dimension. Okay, so then here's the rules for the FANS method. The rule number 1, you choose the model with the minimum dimension, right? So that's because that's your criterion of optimality. Well, so then you say, what if they're ties? Okay, in some cases you could end up with more than one model within the FANS with the same dimension. So which one you choose? Then you say, okay, in that case I choose the model that fits better. Make sense? Yeah. So they're tied in terms of dimension, both in the FANS, and I pick the model that fits better. Okay. So that's the rule number 2. Okay. Okay. Now, if you stay with this rule, it turns out that no matter how you choose this cutoff, okay, you can choose it adaptive. You choose it adaptively, as I showed you with that little curve, in which you can end up evaluating many different cutoffs, but only a few models are possible results of a selection. Okay? So you look at all the models, I'm telling you, only a few models even have a chance to be selected. Then you say, who are these lucky guys? Well, here's an example. Suppose the maximum dimension of the candidate models is 3. Okay, so you only look at models up to dimension 3. Okay, so now I'm using this notation, mj to be the model with dimension j, such that this measure of lack of fit, this model minimizes the measure of lack of fit among all the models with dimension j. Okay, so that's the mj. So basically, you see here, because all my models have dimension at most 3. Okay, first I classify them into 3 groups: models with dimension 1, models with dimension 2, models with dimension 3. Okay, among each group, I'm going to pick the top candidate according to whoever does the best in terms of model fitting. Okay, but here you only compare models with the same dimension. Okay, so there's no such problem that you have to choose between a model with 3 dimensions and a model with 100 dimensions, as in my earlier example. You don't have to worry about that because everybody has the same dimension. Okay, it's easy to pick the top guy, okay, whoever does the best in terms of model fitting. Okay, so you choose those guys. So these are the lucky guys that I mentioned. Okay, the other guys don't even have a chance. Okay, so that's the point. Okay, so that's easy enough. Sometimes it's a lot easier when you explain things in terms of common sense. But once you have to write out some mathematical formulas, it becomes a long expression. So let's skip them. All of these things do the same thing as what I just said. Okay, so as I said, the other guys don't even have a chance. So all these guys these are the only 4 models that have chance to be selected as the optimal model. So now your job seems to be a lot easier, right? From maybe choosing from hundreds of models now down to 4 models. Okay, so still the question remains, which one? Okay, because you want to choose one model, not all 4 of them. Okay, so who is this lucky guy? Well, to solve this problem, we use the idea of the adaptive fence. Remember this little curve I showed you? Okay, the idea is that you calculate the empirical probability that each model is selected. Okay, whoever has the highest empirical probability, and that's the guy. That's the lucky guy. Okay, here you got 4 models, right? You can also calculate the empirical probability for each model, and whichever has the highest empirical probability is the model you select. Okay, so this idea is very similar to the adaptive fence, which I like to skip. Okay, this tells you how to compute this empirical probability. If I have time, I can explain it a bit more. But you can also read this paper, this 2008 paper. It illustrates this idea of the adaptive fence. Okay, so now here's the link between this method I just introduced with the fence method. You see here, we don't seem to have a fence, right? Where's the fence? You pick the model that fits the best within each dimension. Then you calculate the empirical probability. It doesn't seem to have this fence inequality involved anywhere, right? So why is it's called a fence method? It's still called a fence method. Well, the reason is it actually uses implicitly the principle of the adaptive fence. So for such a reason, the new method is called invisible fence, or IF. So once again, let me rephrase the link between this invisible fence and the original fence method. So the idea may be interpreted as finding the model that has the best chance to best fit the empirical data when controlling the dimension of the model. Okay, so it has the best chance to best fit the empirical data when controlling the dimension of the model. So this last sentence is important because if you don't control the dimension of then the largest model always wins. Okay, if you don't control the dimension, whoever fits the best, the largest model, you always fits the best, therefore always wins. However, if you control the dimension, it's a different game. Because this same idea has been used in many other model selection criteria. So this is consistent with the principle of the adaptive fence, provided that the minimum dimension criterion is used in selecting the models within the fence. Okay, so this is this is a brief description of the invisible fence method. Okay, now I'd like to apply this method to the microarray gene set analysis problem that I discussed earlier. So, remember we have this this measure of lack of fit. Okay, so basically you want to say why you can. So here's the first question you want to answer. So how do you connect model selection with the gene set identification? Okay, so where's the model? Right. So that's one thing. Another thing is what is the measure of lack of fit here? Because what is the measure of lack of fit here? Okay. So before I answer that question, let me point out one special case, which is when there's no parameter involved under the assumed model. Okay. So the general form of this measure of lack of fit allows you to involve three things. One is the candidate model. So capital M represents the candidate model, and the Y represents your data, and this here theta M is the parameters under the assumed model. Okay, so under this model, these are the parameters. So this measure of lack of fit can involve three things, but in some cases, it doesn't depend on any parameters, such as in our case. So in this case, the calculation of this measure is a lot simpler. Okay. Now, luckily, for the gene set analysis, it belongs to the last case where it doesn't involve the parameter theta m. Okay. Now, here's the next question. Now, how do you define a model for gene set analysis? Now, here's an example. Suppose there are m gene sets under consideration. These are the candidate gene sets. Okay. And these gene sets are denoted by the numbers from 1 to m. Okay, so then you say, what is a model? A model corresponds to a subset of these numbers. Okay, so any subset of these numbers correspond to a model. And for example, 1, 3 is a subset. Okay, that means you would identify gene set number 1 and number 3 as your differentially expressed gene sets. Okay, so any subset of these m numbers is considered a model. Okay, so a model corresponds to a subset. So then models, the subset selection becomes a model selection. Therefore, gene set identification becomes a model selection problem. Okay, this was the original idea that proposed by Dr. Rao. Okay, so that's the idea. So in this case, a model is completely specified by the subset, and there's no other thing involved, such as parameters. There's no parameter involved. Okay, now here is a practical problem that we have to solve before we do anything, because our intention is model selection for high-dimensional data, and this is a particular case of high-dimensional model selection problem. So for that kind of problems, the number one issue you have to deal with is computation. Okay, so let's just consider one example. Okay, remember that paper I mentioned earlier about the 2005 paper, okay, in which they have a example that involves 522 gene sets. Okay, now if you have to consider all the subsets of these 522 gene sets, the total number of subsets is 2 to the 522. Okay, that's an astronomical number. Okay, so how can you afford to evaluate such a huge number of gene sets? Okay, because you have to evaluate this measure QM, right? You got 2 to the 522 evaluations. Okay, so So that problem you have to solve, right? So that's why whatever you do, you have to first you answer this question. Yeah, so that's the one I just talked about. 522, yeah. So in 522, you get let's say, okay, here's a little calculations. If you're just going to consider all the subsets that have two gene sets, okay, k equal to 2. The total number is 135,000, okay, sorry, 136,000. So now you say, okay, what if I have to consider all the models with 3 gene sets? Well, the number increases quickly, okay? Right? So then you say, okay, if I have to consider all the subsets, then you get a 2 to the 522. That's what I mentioned. Yeah. So how do we solve this computational problem? Well, here comes an advantage of the Fence method. That is, you remember this measure of lack of fit, QM, right? Now, I didn't say what the QM has to be, right? Well, as long as it makes sense, it could make a good measure of lack of fit. Okay? If you choose that gene set appropriately, it could save you a lot of computations. Here's an example which makes total sense in this situation. Okay? So let's consider the situation where there are a large number of candidate elements, such as gene sets, variables, such that each candidate model corresponds to a subset of something. Okay? If you say you can call them candidate elements, but basically it's a subset of something. Okay? So then, if you are in this situation, you can define a measure that fits to this case very well. Okay? So here's the definition. A measure is said to be subtractive if it can be expressed in this way. So basically, is some constant subtract something, which is a summation. Okay, and inside the summation, there's a term corresponding to each candidate element that is involved in this subset, M. Okay, so remember M is a subset of indices, right? So what you do is you take the summation over the subsets of the indices of the corresponding to the candidate elements in the subset. Okay, and you subtract that from an overall constant. Okay, so that's why it's called subtractive, because if you don't look at this, if you cover the first two terms, then it would be called additive. But because you're subtracting the sum, it is called subtractive, not additive. Yeah, because so here's another way to look at it. Every time you add an element to your model, you subtract a quantity corresponding to that element. Okay, so this kind of measure is called subtractive. Right? Then you say, what is the advantage of a subtractive measure? Well, the advantage is that if a measure is subtractive, then I can immediately find the model that minimizes this measure at each dimension. And you say, how? Well, here's how. First, I rank those candidate elements in terms of this decreasing SI. Okay, remember, there's a SI corresponding to each candidate element. Okay? So just say, suppose those candidate elements are gene sets. Okay? I have a gene set statistic, SI, corresponding to gene set I. Okay? I rank them in terms of decreasing SI. So then I can answer that question immediately. Okay? The model that minimizes QM at dimension 1 is the guy who is not ranked number 1, because it's decreasing, right? Decreasing order. Okay? Then the largest element is the one that minimizes QM at dimension 1. Why? Because just think about it. You have to subtract one element. Whoever is largest, when you subtract, you get the smallest QM, right? So that answers the question of dimension 1. Then you say, how do I find the QM, the model that minimizes QM at dimension 2? Well, that's number 1, number 2, right? Because you have to subtract 2 elements. When you subtract the top 2 elements, you get the smallest reduction, okay? And so on. So with this algorithm, you find those QMs at different dimensions right away. Okay, now here's the example associated with the gene set analysis. Suppose the SI is let SI be the gene set statistic known as the gene set score corresponding to the ith gene set. For example, SI may be the max mean statistic proposed by Efron and Tipshrani. And here's a description of how to compute the max mean. First, you obtain the positive and negative parts of each gene-wise summary statistic. So here's the mathematical definition of the positive and negative part. So then you take the means of these positive and negative parts, okay, and then you call them S bar plus and SI bar minus. Okay, so then you take the maximum of these two. That's what we call max mean. Okay, so just an example of SI. So let's just say we use this SI. Then you can define a subtractive measure QM by this earlier equation number 4, with SI being the max means. Okay, so that's just an example of a subtractive measure. Since I have limited time, let me jump to an example of a simulation study. Okay. So there are some practical issues that we have to solve when implement this method. But since I have limited time, I would skip those and show you this simulation study. Efron and Tipshrani, in their 2007 paper, carried out an empirical study in which the authors simulated 1,000 genes and 50 samples in each of 2 classes, control and treatment. The genes were evenly divided into 50 gene sets, with 20 genes in each gene set. The data matrix was originally generated independently from the standard normal distribution. Then the treatment effect was added according to one of the following 5 scenarios. Okay. In the first scenario, all 20 genes of gene set 1 are 0.2 unit higher in class number 2. Remember, class number 2 corresponds to treatment. In the second scenario, the first 15 genes in gene set 1 are 3.3 units higher in class 2. So then there are some other scenarios that were considered. Okay. Now we considered the same 5 scenarios in our simulation study. In Efron and Tipshrani's study, only the first gene set is of potential interest, because they only considered one situation where there's a single gene set that is differentially expressed. Now we expand their 1 gene set case to a 2 gene set case in which we duplicate the 5 scenarios to the second gene set. Also in Efron and Tipshrani's study, the genes were simulated independently. We also considered a case where the genes are correlated with equal correlation that is equal to 0.1. This describes how you generate the correlations. We basically use the mixed effects model to generate data with the correlation, which I have to skip. Okay, so then we compare the performance of IF. IF means invisible fence, with GSA in gene set identification. In the Efron Tiptrani simulation study, the authors showed that the max mean, the one I discussed earlier, has the best overall performance as compared with other methods. So therefore, our comparison focused on the best performer of GSA, that is the max mean. In addition to the 1 gene set and 2 gene set cases, each with 5 scenarios listed above, the simulation comparison also includes a case where there's no gene set that is potentially of interest. Okay, so we consider 3 cases: no gene sets, 1 gene set, and 2 gene sets. The number of permutations for GSA is 200. That's the number that Efron Tiptrani used. The number, the invisible fans requires a bootstrap procedure in order to get the empirical probability. Remember that empirical probability actually was obtained by bootstrapping. So that the number of bootstrap samples is used. That are used as is 100. Okay, now here's the first set of comparisons. Is on the probability of correct identification of truth positive. And what it means is that you identify exactly those gene sets that are differentially expressed, no more and no less. So that's called truth positive. And here's a table. Let me explain this result. Okay, so there's little numbers shown here. Okay, so these numbers are the empirical probability of truth positive. Okay, and of course, the higher the better. But there's also there are also numbers in the parentheses. So these indicate the probability of overfit and underfit. Okay, so the first number is overfit. The second number is underfit. Now, from this table, you can see that the IF method performed consistently better than the GSA method. Okay, in some cases, significantly, and this is uniform according to uniformly across all the cases and the scenarios. Yeah, so that's what I just said. Now I have some other summary statistics in terms of the mean of the mean of correctly selected gene sets and mean of incorrectly selected gene sets, as well as the standard deviations. But I'd like to show you my final set of simulation results, which focus on this, a property we call signal consistency. Here's what I mean by signal consistency. Traditionally, consistency in model selection, model identification, including parameter estimation and model selection, involves sample size going to infinity, right? So that's what we call statistical, in statistics we call what we call consistency. But here, this assumption is not very realistic in gene set analysis because the sample size is usually much smaller than the number of genes under consideration. So you're saying sample size going to infinity, it may not be so practical in this situation. Okay, so what is a more practical consideration? And here's what we consider called signal consistency. So basically, a gene set identification procedure is signal consistent if its probability of truth positive goes to 1 as the treatment effect or signals increase to infinity. Okay, basically, it says that you will be perfect in perfect situations. Okay, so that's what it says. You're perfect. You will be perfect in perfect situations. Okay, so we think that's quite basic. Okay, if you're not perfect, even in perfect situations, your method has a problem. Right? Your method has a problem. So basically, that's what it says. Then you say, okay, of course, this perfect situation never happens in the practice. Yeah, I agree with you. Things never happen, right? But you have to define something, ideologically, right? You have to have something in your mind, right? So what is the target to work on, right? Even if you cannot achieve it in practice, okay? So once again, one may not be able to increase the signals in real life, but the point is to see if a procedure works perfectly well in the ideal situations, which we believe is a basic property, just like consistency in the traditional sense. To investigate the signal consistency property of IF and GSA, we expand one of the scenarios, namely the last one, by increasing the treatment effects in two different ways. First, we increase the signals in a balanced manner. That is, the signal increase at the same pace for both gene sets. Okay, we consider a two gene set situation. We add signal to both gene sets and let the signals increase at the same pace for both gene sets. So this is what we call the balance case. Next, we consider increasing the gene set in an unbalanced manner so that the pace is much faster for the first gene set than for the second one. So basically, here's what we do. Okay, we consider these numbers A, B, C, D that increase, that indicates what signal you add to part of the gene sets. Okay, so A is the signal that adds to the first 10 genes of gene set 1. B is the signal that adds to the second 10 gene sets of gene set 1. C is the signal added to the first 10 genes of gene set 2, and D is the signal added to the last 10 genes of gene set 2. The case 1, okay, so let me show you the results. So here's what happens when the gene signals increase. So here's the comparisons of the probability of truth positive. Okay, so in the first three cases. Okay, case number 1 is the baseline, because this result is taken from that earlier paper, because that last case we considered. Okay, from that baseline we start to increase the signal. Here we increase the signal at the same pace. See, from 0.4 to 0.5, then from 0.5 to 1.0. Okay, simultaneously in the balanced pace. So then you can see the probability of truth positive increases in both cases. Okay. So that means both methods are signal consistent in this situation when you increase the signal in the balanced pace, in the balanced manner. So then start from here, we begin to increase the signal in an unbalanced manner. Okay, you can see the signal increases much faster, at a much faster pace for the first gene set than for the second gene set. Okay, so you see basically here increase to 0.5, increase a little bit, but then you stay there, you let the first one increase. Okay, so here's what happens. When you do that, well, the probability of IF still stay as 1. Yes, it's still 100% probability. But what happens is that for the GSA, the probability of truth positive begins to decrease and eventually vanishes. Okay, so you wonder why is there such a problem? Okay, you see, in the first case, everything seemed to be okay. Then all of a sudden, GSA seemed to have collapsed. The reason is that there's a problem with the restandardization. Okay, so why is this a problem? I mean, explain intuitively using the last 1 minute or so. Okay, and just consider how you standardize your statistics. Right? Well, basically you subtract the mean and divide by standard deviations. Okay, now suppose among your data, there's one guy that dominates, and it is so dominant. And once you subtract that guy from the mean, once you subtract that big guy, every difference becomes negative except one. This can happen, right? You get a, let's say you have 10 numbers. The first 10 numbers are 1, the last one is a million. When you subtract, everybody gets negative except the last one, right? And then when you standardize this thing, most of them are negative, right? However, if you use the permutation to get critical values, okay? Usually your critical value for any reason under any reasonable FDR should be at least non-negative, right? So you're looking at a standardized statistic. The critical value, any reasonable critical value should be at least non-negative. But in your real data, all of them are negative except one. So this means no matter, you can only identify one guy, because that's the only guy who is positive. The rest of them are negative. Okay? No matter how much you increase the signal, as long as you're in this situation, there's only one guy that gives you a non-negative standardized statistic, and the rest of those are non-negative. So in this extreme case, GSA can collapse, and that's the reason. And the IF method does not have this problem. Thank you very much.